Hello everyone. Today I will talk about the paper FuzzyNet, a fuzzy attention module for polyp segmentation by Krushi, Patel, Dr. Lee and Dr. Wang from the University of Kansas and Toronto Metropolitan University. Polyp segmentation is essential task for accelerating the diagnosis of colon cancer, as colon cancer starts with the development of the polyp. It is very challenging task because of polyps' diverse color, texture and varying light effect. In addition, it is very difficult to differentiate the polyp and its surrounding area because of the subtle difference between them, especially around the boundary region. In this work, we propose the attention module to tackle the issue of difficult pixel around the boundary region. There have been some methods proposed to solve the problem of difficult boundary pixels, but they require extra boundary annotations and they do not generalize well. In addition, some attention-based methods have been proposed which concentrate on the background pixels to mine the difficult boundary pixels. We believe if we directly give more focus to difficult boundary pixels, the performance can be further improved. Here is the overall architecture of our network FuzzyNet. It consists of a series of convolution layers, partial decoder, which generates the global map, followed by a series of proposed fuzzy attention modules. We apply deep supervision at the end of each fuzzy attention module and partial decoder. The main module of the network is fuzzy attention module, which I will explain in the next slide. The fuzzy attention module takes the input from the partial decoder and applies sigmoid activation and reverse attention to calculate the forward and reverse attention map. Forward attention map has a higher score for polyp pixel, whereas reverse attention map has a high score for the background pixel. After that, we calculate the absolute difference between these two scores. The lower the difference, higher the difficulty in the classification of pixels. To give more score to this difficult pixel, we further apply reverse attention to this absolute difference. The resultant map is then multiplied by the corresponding encoding layers feature. We embed our attention module in three different backbone networks: REST2Net, ConvNext, and Pyramid Region Transformer. We report the performance on various datasets to verify the learning and generalized ability of the model. We use binary cross entropy and IOU loss during the training. We have used total 5 different datasets: Kvasir, CVC-ClinicDB, CVC-ColonDB, CVC-300, and ETIS. The total number of images per dataset has been displayed in the parentheses. We made two types of dataset split. One is to prove the learning ability of the model, and second is to prove the generalization ability. For learning ability, first Kvasir and CVC-ClinicDB datasets are merged, shuffled, and then divided into train and test set. For generalization ability, we kept the same train set as the learning ability, but test sets are different. Test sets come from the CVC-ColonDB, CVC-300, and ETIS datasets. Here is the result on CVC-ClinicDB and Kvasir dataset in terms of mean DICE and mean IOU, which shows the learning ability of the model. If you compare the performance of PraNet and our model with REST2Net as a backbone network, it can be seen that our model outperformed the PraNet by significant amount on both datasets, which shows the effectiveness of our attention module. With PVT as a backbone network, our model achieved highest performance compared to the latest method on both datasets. Here is the result on remaining datasets, including CVC-ColonDB, ETIS, and CVC-300, which shows the generalization ability of the model. Again, if you compare the performance of PraNet with our model with REST2Net as a backbone network, our model significantly improved the performance on all datasets, which shows the generalization capability of the fuzzy attention module. With PVT as a backbone network, our model achieves state-of-the-art performance on the CVC-ColonDB and ETIS dataset. Conclusion. Our paper has presented a novel attention mechanism to encourage the network to focus more on the difficult region. We embed our attention module with various backbone networks, REST2Net, ConvNext, and PVT. Our result shows that Fuzzy attention module significantly outperforms the PraNet, which employs the reverse attention. With PVT as a backbone network, our model achieves state-of-the-art performance on the CVC-ClinicDB, CVC-ColonDB, and ETIS datasets. Thank you.